In this example, the signal xt is given and we are asked to determine its exponential Fourier series coefficients. Let's begin by sketching the signal. From 0 to 1, the signal has a constant value of 3/2. From 1 to 2, its value is minus 3/2. The first important point is that Fourier series coefficients are defined only for periodic signals. Therefore, we consider this waveform as a periodic signal that repeats every 2 seconds. From the graph, we immediately identify the period as 2. Since the period is 2, the fundamental angular frequency is equal to p. Now let's calculate the Fourier series coefficients. Recall that the exponential Fourier series coefficient AK is given by 1/t multiplied by the integral over 1 complete period xt e to the power of minus jk omega 0 t with respect to t. Since the period t is equal to 2, the coefficients becomes 1/2 the integral over 1 complete period A Fourier series integral may be evaluated over any interval of 1 period. Here we choose the interval from 0 to 2. Within this interval, the signal consists of 2 constant sections. From 0 to 1, the signal is 3/2. From 1 to 2, the signal is minus 3/2. Therefore, the integral is divided into 2 parts. The first integral extends from 0 to 1, and the second integral extends from 1 to 2. Before continuing, let's recall another useful integration formula. The integral of e to the power of theta t with respect to t is equal to 1/theta times e to the power of theta t. Now we apply this formula to both integrals. We also write 3/2 instead of 1.5. Combining the constant coefficients, 3/2 multiplied by 1/2 becomes 3/4. Taking this constant outside the integrals, we evaluate both exponential terms at their corresponding limits. Now let's simplify the exponential term. Using Euler identity, e to the power of j theta is equal to cosine theta plus j sine theta. Since cosine of 2 copy is equal to 1 and sine of 2 copy is equal to 0, the exponential term e to the power of minus j 2 copy is simply equal to 1. After simplifying, we recognize another well-known Euler identity, which related exponential functions to the sine function. Using this identity, the final expression for the Fourier series coefficients becomes 3 divided by copy multiplied by e to the power minus j copy over 2 times sine of copy over 2. This is the final closed form expression for the exponential Fourier series coefficients. Now let's compute one coefficient as an example. Suppose we are asked to find A3. We simply substitute k equal 3 into the final equation. This immediately gives the value of A3. This example demonstrates how to determine the exponential Fourier series coefficients using the integration formula. Along the way, we reviewed how to determine the period of a periodic signal, calculate the fundamental angular frequency, evaluate the Fourier series integral, and simplify the result using Euler identities. If you found this tutorial helpful, please like the video, subscribe to the channel, and stay tuned for more solved examples on signals and systems and Fourier series.